Hello, welcome back to our course on advanced quantum mechanics. This is lecture 11. Where are we in the course? Well, from the Hamiltonians, we know how to go down the hierarchy of abstraction to the equations of motion, canonical commutation relations, and hermiticity conditions. And then we saw methods for solving the equations of motion and the other conditions. T and the p hat of t, etc., f hat of t. And we found that these are linear maps. Linear map valued functions. We were open-minded about this. We said everything in math can be represented as a map. So therefore, whatever the x hat and the p hat are, they should be map-valued functions in some sense. And we found that we get away with linear maps. Great. Then we found out how to boil these linear maps down to number-valued predictions. So x bar of t and p bar of t and eventually f bar of t. And for this purpose, we introduced an initial state vector psi that describes the initial conditions that our system is supposed to have. And we found that this linear state vector psi is an element of a Hilbert space. Notice that here I used on purpose language and notation that did not refer to a basis. See, these x hat, p hat, f hat are linear maps. For every point in time, these are linear maps, mapping vectors of a Hilbert space into vectors in a Hilbert space. And this is the level on which the physics is happening. The level on which the calculations are happening is usually a little bit more concrete. Namely, in practice, it is usually useful to introduce a basis. Because then, instead of working with abstract maps and abstract vectors, we're going to work with abstract coefficients and coefficient functions. And then we can do things like integrating, summing, differentiating, and so on with these explicit functions. So we have a lot of tools at our disposal for actually doing those steps explicitly, solving the equations of motion, and then finally calculating the predictions. So in practice, it is useful to use Hilbert bases. Remember, in infinite dimensional vector spaces, we have to be a little bit careful here with bases, and that's why we introduced the notion of Hilbert bases carefully. The infinity of the bases means that we have series to consider and issues of convergence and completeness, and that's why we upgraded from vector spaces to vector spaces with more structure, namely complex vector spaces, and then inner product spaces, and then by completion, Hilbert spaces. And those have Hilbert bases, orthonormal bases that span the Hilbert space. Now, for example, these Hilbert bases could be called, e.g., they could be called the Hilbert bases of the Bn vectors, let's say, just to give them a name. And the index n might run through the natural numbers or the integers or any other discrete index set. Or, for example, a basis of vectors Cn, which might also form an orthonormal basis, and in particular a Hilbert basis, where also this is running through an index set. In fact, the index set may not be the same. For example, it could be the Bn basis vectors have an index that runs over all the integers, positive and negative. It could be that the Cm have an index set of m's that run only over the natural numbers larger than 320. Why not? There are just as many positive numbers as positive integers as there are negative integers as there are integers, right? Because countable infinite is countable infinite. This is what is demonstrated by Hilbert's hotel, for example. So we can choose any one of these bases, and then we have, and this is the point of having Hilbert bases, that if the Bn and the Cn are Hilbert bases, then any vector psi in the Hilbert space can be written uniquely as the sum over n and then coefficients psi n times the basis vectors. But similarly, there is also a decomposition as a series in coefficients that we may call psi tilde m, just to invent a name, Cm. Right? So the same vector, psi, can be expanded in any Hilbert basis, and we get coefficients psi n that represent our vector, or psi tilde m, or whatever we may want to call them, considering the basis that we may want to choose. All right, so we also briefly discussed and more about that will come soon in the course. We also briefly discussed that there exist continuous bases. A lot needs to be said about that, but I'll say these things later. For now, let's say, give an example, e.g., we may call such a continuous basis a basis of vectors up. Let me let's just use more space. For example, a basis of vectors d with an index mu, and that index mu could be, all values mu in some range R, which is a subset of the real numbers. So R is just a name. Let me just change that so that it's not confusing. Let's call this D. Okay, so mu is some set of real numbers like an interval. It's a continuous set. It could be mu could be running through all the reals, or just the positive reals, or just from 1 to 5, or anything like that. So we can also have these continuously labeled bases. That's the point, continuously labeled bases. The trouble is that technically speaking, as we will discuss later, these guys are not elements of the Hilbert space. They're not normalizable. But there's a continuum of them. And then we have, just like we had up here, the psi can be expanded in terms of the Hilbert basis of the Bn. We now have that our vector psi in the Hilbert space can also be expanded in the basis of the d mu as a linear combination, but it's going to be a continuous linear combination. And we're going to have lots of coefficients that will have the label, here the label psi, the label was n of psi, and that's a discrete label, but now we have a continuous label mu here, and we would integrate over the interval d, which may be the real line, d mu. As I said, we haven't properly defined what these things are, and what the integration over vectors is, but for now, let me just tell you that this can be properly defined. So this is structurally very similar to what we have here underlined in yellow. So this is an integral instead of a sum, instead of a series, but other than that, it's very similar. However, notice that notation, we often write these continuous representations in a slightly different way. We write instead the psi equal to the integral over whatever the range of the mu is, and then we write psi of mu. And then we would write just mu, and then d mu. It's of course exactly the same. This is just by definition psi of mu. So for every mu, you associate a complex number. And this is then by definition just mu. For example, this could be position vectors or so. As we will later see, I don't expect you to know exactly how this works in this framework just yet. All right, and let me remind you about terminology. So, terminology. The sets of coefficients psi n that we had up here, you know, the coefficients psi n of the expansion of our state in the B basis, and the psi tilde m. These are the expansion coefficients of our state psi in the C basis, but also these coefficients psi mu, where all the mu are ranging through D, are called the wave functions of our state psi in in the basis Bn in the first case, and the basis of the Cn for the second case, and in the basis of the d mu for the third case, so respectively. All right, so in this case here, where we have psi index mu, which we also write as psi of mu, this is the most plausible, right? That we call this a wave function because it looks like a function, psi of mu. It's really just a coefficient. It's really just the collection of coefficients of our vector psi in a basis. But since it assigns to every mu a psi, we can call it a function, a wave function. But the basis doesn't have to be continuous for this label, for this name. We can also call the psi tilde m, which map every m into a complex number, a function. It's just mapping a discrete set into numbers. And that's a wave function as well. So wave functions can be defined on a continuum, but wave functions can also be defined on a discrete set of points. Let's make a little observation which will lead to a very useful trick. Remember this equation that's underlined in yellow here. Let me write it out again below. So we have recall, we have that psi is expandable in the Bn basis as psi n Bn. And recall that these basis vectors are orthonormal. So we have Bm, Bn is delta n m by assumption. Well, then we have that if we apply the Bm from the left, then we have Bm applied to the left-hand side to the equation is equal to, well, Bm applied to the right-hand side of the equation. So sum over n, looks like an m, should be an n, and then psi n Bn. But all of this is linear, so we can write here the sum outside, and then we have Bm, and then we have psi n and Bn. Now this, remember, is just a complex number. It's the coefficient here in the basis, right? So we can pull this complex number out of this. So we obtain that this is sum over n, and then psi n, the complex number that we pulled out, and then we have psi, oh, not psi, b. And we have here b, m, b, n, which is sum over n, psi n, delta m, n. We are summing over all n, and of course the Dirac delta, the Kronecker delta here only gives one contribution, and we obtain that this is psi m. All right, let's mark this and let's remember it. I think we had this before, but let's put that here. Okay, so the wave function, in other words, the wave function of a state in a basis, so in a basis, the wave function of a state is given by the inner product between the state and the basis vectors. Okay, so wave function is given by inner product or scalar product of state psi with basis vectors Bm. Right? Remember that the psi m form the wave function of our state in this case in the Bn basis. All right, now from that we obtain directly a very useful tool, namely resolution of the identity tool. Resolution of the identity. This will be a very useful resolution for bridging between abstract formulations and concrete formulations. That is to say, basis independent formulations and basis dependent formulations of our equations. So we begin with this. We start with what does a vector Bn, a Bra vector Bn, what does it do? What does this do to a vector psi in H? So this thing is, of course, in H star, the dual Hilbert space. So what does this do? Well, we just calculated it. Bn applied to psi is equal to equal to psi n, and therefore it is a complex number. So then we can ask, so what does this thing do? Bn do to psi? Well, let's work it out. Straightforward. We have that Bn applied to psi is what? Well, this is an element of C. It's a complex number, right? So this whole thing here, which is psi n Bn, is an element of the Hilbert space. It is just a multiple of the vector Bn. Now, let us ask, so what does this thing do? Sum over n, and then we take all of the Bn. By the way, I should clarify that when we just specify the n as the summation variable, then it's always implied, if not otherwise stated, it's always implied sum over all n, whatever that might mean. Because for some Hilbert bases, the n might run just over the positive integers, or just over the negative integers, or just over integers larger than 270 or whatever. So what does this thing here do to psi? Well, let's work it out. You have sum over n, and then bn, and bn, and you may already see where this is going. This is going to be, since this here is the psi n, this is sum over n, psi n, bn, but hey, we know what that is. That is psi, right? Because this here is the representation of psi in the B basis. So what we see here is that the action of this thing here, on any vector psi simply reproduces psi again, right? So we run this sum over the Bn, the ket bra, Bn. If we apply that to psi, we just get back psi. That is a resolution of the identity. In other words, this thing is the identity map. So therefore, we have that the sum over n, Bn, is equal to the identity. And since it doesn't matter which basis we choose, in any other basis, we can write sum over m over the Cm. It's also the identity map. By the way, we will soon switch, well, pretty much from this lecture, to another terminology as well. Linear maps are also called operators. So when we say operator or when we say linear map, it's the same thing. Usually, we use the term operator when the Hilbert space is infinite dimensional. Otherwise, we might just call it a map. But of course, it's they're really synonymous, the two. Okay, and then remark. If we choose a continuous basis, then we would have that the integral, or d, of d mu is also 1. So that can be done as well. But we are going to focus here on the Hilbert bases, which is to say the bases that are countable, discrete bases, where the basis vectors are proper vectors in the Hilbert space, which means, of course, that they are of length finite, that they are finite length. I mean, all the vectors in the Hilbert space are of finite length. Exactly all the vectors of finite length are the Hilbert space vectors, remember? And in particular, the basis vectors are not only of finite length, they are of length 1, because they are also normalized. So that's the case that we will focus on, and for the moment I'm just remarking on what happens with the continuous bases, but we will not delve into that deeper here. So now having these resolutions of the identity, oh, I didn't actually spell it out. So these are we call this resolution of the identity in a basis. You know, as the case may be, the B basis, the C basis, the D basis, or whichever the basis. I should close this quotation mark. So this is what we call this. Now, how is this useful? I promised that it would be useful for turning equations that are abstract into equations that are concrete. So useful to bridge between abstract and concrete. By abstract, we will mean basis independent, and by concrete, we mean dependent on the choice of bases. So, for example, the norm of a vector, the length of a vector, therefore, the norm of a vector. Well, in principle, we can write that the norm of a vector psi is given by this, right? That's the norm of a vector. Remember inner product space, Hermitian conjugation, and all of that. This is the scalar product of a vector with itself. Therefore, it is the length squared of it. Sorry, this is, and then we take 1/2 of that, right? But in order to evaluate this, how do we evaluate this? So now in a basis, remember that this, what I just wrote down, it does not refer to any choice of bases. This equation here that I'm underlining here, this equation is the same, whatever basis you may want to work with. But now, how do we express that equation? How do we express that norm in a basis? Well, there we have to work out what is psi. And the trick now is to use a resolution of the identity in the basis that we want to work with. Let's say we want to work in the B basis. Then we write it like this. It is the prayer, psi, and then we write here the identity map, or the identity operator, psi. Surely we have not made any mistakes so far, because we just put the identity here. What does it do? It acts on psi and outputs psi, the identity map. Okay, but remember that the identity can be written as a sum of brackets of ket bras in the B basis. So we can write this as psi, and then sum over n, and then here's the resolution of the identity from above. This is an n here, and then psi. So we can write this as psi, and then, oh, let's put the n outside, the sum over n outside, and then it's psi, bn, psi. Let's identify what we have. This is the wave function of psi in the B basis. Here are the coefficients of that wave function, psi n. And what is this? Well, this is psi n star, the complex conjugate number. Why is that? Well, because the psi and the bn have traded places. Remember, from our Hilbert space axioms that when you have two Hilbert space vectors, let's call them V and W, and you take the inner product, then this is the same as if you take WV, except you get a complex conjugation here. All right, that was part of the axioms here. All right, so we obtain that the length squared of a vector is therefore given by, in the B basis, sum over all n, psi star n, psi n, as it should be. As we know it from linear algebra, for example. Now, to require that vectors are normalized means something very concrete. So requiring normalization so that psi is equal to 1 means in a basis that the sum over the n, psi star n, psi n equal to 1. It also means that the Hilbert space condition takes a similar form. Recall. Handwriting. Recall. The Hilbert space H consists of all psi, so that for whom it is true that their length is not infinite, i.e., in a basis, the psi that are in the Hilbert space are those that obey that the sum over n, psi star n, psi n is not infinite. All right, so I was claiming that the resolution of the identity will provide us with a bridge between the abstract basis-independent representations and the concrete basis-dependent representations. And here is a summary then of this. Summary. We have that the abstract psi is the sum over the n, psi n, bn, where this is abstract, that is to say basis independent, and this is the wave function, which is concrete wave function, and it is basis dependent, because in every basis it will be a different wave function, basis dependent. All right, so here we are expressing the abstract in terms of the concrete, but we also saw that the psi n is equal to bn psi. And here you see that we are expressing the concrete in terms of the abstract, in terms of the psi. Okay, so we go, here we go from the concrete to the abstract, and here we go from the abstract to the concrete for vectors. And we achieved this by using the resolution of the identity. I mean, it's easy to check these things by using the resolution of the identity as we did above. But How does this look like now for linear maps? Now, bridge between abstract and concrete for linear maps. So, for example, consider the linear map f hat of t. Right? That's some solution to our equations of motion. Maybe an angular momentum, the energy, maybe the position, maybe the momentum. So this is the abstract thing. In a basis, it's going to be a matrix. In a Hilbert basis, it's going to be a matrix. In a continuous basis, it's going to be not a matrix. It's going to be something else. You will see what it is later. But for now, we work with the Hilbert basis, where this, in a basis, is a matrix. How do we go back and forth between this abstract formulation and the matrix formulation? So we can use the resolution of the identity for this. This is identity map acting on f hat of t and an identity map. We have not made any mistakes so far, right? Because we just put identity maps in there, so we haven't really done anything. Now, these identity maps, however, can be expressed in terms of resolutions of the identity. So this is the sum over R and S of BR, B index S. That's, oh no, sorry, not S. It's another R here. R. This is the resolution of the identity here, the first identity. And then we put here our f hat of t. The t dependence doesn't really matter in this. And then we have the b subscript s, b subscript s. All right. What we now see is that this is number valued, right? This is in C. And we will call this thing here, we will give it a name, it's f hat of t, but the matrix coefficients, the so-called matrix elements, are S, okay? So these are the concrete coefficients of our linear map in the basis of the B. So we can write this as f hat of t is equal to sum over the R and the S, and then it's, well, we can write it, for example, as f hat of t rs, and then br bs. Okay, so what we have achieved here is that we expressed, oh, this was a definition here, so we expressed the abstract operator here on the left, the abstract linear map, in terms of its concrete coefficients, its concrete matrix elements in the basis of the B. Remember that this sort of thing here, a ket bra, is always a linear map, because when it acts onto a vector, let's say psi, then the bra here forms an inner product with this vector, gives us a complex number, and then that's multiplied with a vector, so the output is a vector. So this sort of thing always inputs a vector and outputs a vector. So it's a linear map. All right, my point is, this equation here maps the concrete matrix representation of our linear map into the abstract basis independent way of writing f hat, the linear map. And do we have the opposite too? Yes, we have it. It was right up here, right? This equation here, let me spell it out. We also have, and from here, and we have that f hat of t rs, so the concrete matrix elements of our linear map in the basis of the Bn is equal to, wait for it, br f hat of t bs. Why? Well, because that's what we defined up here, right? So we had this thing here. and we call it f hat of t rs. All right, so what we've seen here is that using the resolution of the identity, we can very easily build that bridge between the abstract way of writing an object here, such as the f hat of t, which could be a position or momentum variable or whichever, and its concrete matrix elements in our preferred choice of bases. And clearly we can now also go from one basis to another basis because we can resolve the identity in any basis that we want. Before we change bases though, I have to tell you that there is some subtlety that comes up in this. Because this is not like linear algebra in the sense that our Hilbert spaces are infinite dimensional. And new things happen here. And one of the things that happen because of the infinite dimensionality of our Hilbert space, one of the things that happens is that we have to be careful with what vectors we allow our operators, our linear maps, our f hat, to act on. So I have to say here a word of caution. And we will see that this is physically quite relevant. So because the Hilbert space is infinite dimensional, we have that it is not guaranteed that if psi is in the Hilbert space, then also f hat acting on psi is in the Hilbert space. That's not guaranteed. In linear algebra, if you have a linear map acting on a vector, you get another vector of the same space. But not here. Why? Well, let's consider, for example, f hat rs to be given this matrix. So we are considering now the operator or linear map, which has these matrix elements: 1 squared, 2 squared, 3 squared, 4 squared, and so on, and the rest is 0. Very simple matrix. And it's acting on, let's say, this column vector here: 1, 1/2, 1/3, 1/4, and so on. One might think, easy enough. The matrix is diagonal, everything looks fine. But, let's see, is this all legal? Let's calculate the norm of the vector that we start with. Norm of the vector 1, 1/2, 1/3, is what? Well, it is, okay, let's just write it like this. Psi I is equal to psi n here is equal to 1 over n, right? This is psi 1, so up here. So psi 1 is 1 over 1, right? Psi 2 is 1 over 2, then 1 over 3, 1 over 4, that's always 1 over n. So these are the coefficients of our column vector. So therefore, the norm of our column vector, 1 and 1/2, 1/3, etc. The norm of this vector squared is the sum over all n of 1 over n squared. this better be finite in order for our vector to be in the Hilbert space. So what is this value? As it turns out, people have wondered about this even before quantum mechanics. What is the sum over, or what is the series 1 over n squared? And in fact, a prize was promised for anybody who works out what that is. Because it turned out to be super hard to actually sum up that series. It was the so-called Basel problem, or Basel. Basel is a city in Switzerland. It's the Basel problem. One of our TA's name matches the name of that city, Basel. So the Basel problem. And it turned out that a young fellow by the name of Leonhard Euler was the first to figure it out, about half a century after the problem was posed. So I don't know if he ever got the prize. So Euler found out that this is actually pi squared divided by 6. Euler. Well, of course, you know this is the famous Euler. All right, so he worked that out. And for us, relevant is that this is smaller than infinity, and therefore our vector, 1, 1/2, our vector with these coefficients, 1/3, etc., is in the Hilbert space. Okay, so that's good. Now, let us apply naively this linear map given in the bases by this matrix here on that vector. What do we get then? Well, if we apply that vector, if we apply that matrix on that vector, what do we get? We get a vector whose first entry is 1, second entry is 2 squared divided by 2, that's just 2. The next entry is 3 squared divided by 3, that's just 3. Next entry is 4 squared divided by 4, that's 4. So we see where this is going. We see where this is going. Namely, now we have that the matrix 1 over, well, it's not 1 over, it's 2 squared and then 3 squared, 4 squared, so it's 1 squared, 2 squared, 3 squared, 4 squared, boop, 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 acting on 1, 1/2, 1/3, and so on, is equal to the vector whose coefficients are 1, 2, 3, 4, 5, and so on. Now, is this vector in the Hilbert space? No, it cannot be in the Hilbert space because this vector has what length? Well, you see, the sum of, let's call these coefficients phi n. And then we have that the sum over n of all phi star n phi n is the sum over all n of n squared. Now that's definitely divergent. So we have a problem here. Our operator, our f, was catapulting our vector into oblivion. It mapped it outside of our Hilbert space. No operator is supposed to do this. It can't just map into uncharted territory, but that's what it would do. So therefore, we have to restrict the domain of our operator f. So therefore, we need to, f hat not to act on this psi, right? So notice the situation. Psi is in the Hilbert space. But this operator is not supposed to act on this vector in the Hilbert space. What we have is the following. The maximal domain of any operator, of an operator. Remember, operator just means linear map on the Hilbert space of an operator f hat is, and then we write this d for domain, and then little superscript f hat to indicate its domain. It's the domain of our operator f hat, of our linear map f hat. And by domain, we mean the set of elements of the Hilbert space that f hat is allowed to act on. So the domain of f hat is the set of all vectors in the Hilbert space for which f hat psi is also in the Hilbert space. Okay, so it means f hat, the maximum set of vectors in the Hilbert space that we can allow any operator to act on, is the set of those vectors in the Hilbert space whose image under f hat is also in the Hilbert space. In other words, an operator can only map normalizable vectors into normalizable vectors. If it would map into non-normalizable vectors, we don't do that because it would lead us outside the space of definition here, outside of our Hilbert space. Now, at this point, you may wonder, oh, that's going to be tedious. How do we find out what the suitable domain is? Especially what the maximal domain is? Now, it turns out that sometimes it's hard to identify what the maximal domain is. It's a bit, I mean, usually doable, but it can be tedious. But in practice, you can often choose a safe domain, a domain that you know your operator can act on, no problem. And it may not be the maximal domain, but it may be big enough. So in practice, we can often choose a convenient domain for f hat that may not be the maximal domain, but that is still big enough. Oh, I'm sorry about the handwriting here, but still big enough. Big enough means no vector in H is orthogonal to all vectors in the domain. To all vectors in D. Example. In the above case, where we have this matrix with the Basel problem that Euler solved and all of that, example, in the case of the operator above, so remember its matrix representation was 1, 2 squared, 3 squared, pop, 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 0, 0. We can choose df hat. We can choose a domain, which may not be the maximal one, it's not the maximal, but it's big enough, to be the set of psi in the Hilbert space, all those vectors in the Hilbert space for which it is true that psi1, psi2, has only finitely many non-zero psi I. Okay, so this means we define as the domain of our operator f hat all those vectors psi who in column representation here in our basis of the Bn's are of the form numbers, but only finitely many are non-zero. So infinitely many zeros in there, but finitely many non-zero terms. Why does this help? Well, it means obviously that if our matrix here acts on a column vector that has only finitely many non-zero entries, then clearly the vector that you get when the matrix acts on that is still of finite length, because that's not, we only have to sum up a finite number of terms. So we are fine, it's still in the domain. And yet, it's big enough, this domain, because no vector in the Hilbert space can be orthogonal to all of these guys. Because remember, you can span a basis with these, right? Because, for example, these vectors contain, our domain here contains the vector 1, 0, 0, but it also contains the vector 0, 1, and it contains the vector 0, 0, 1, and the rest zeros, right? So therefore, yeah, they span the entire Hilbert space. And yet, the domain here is not the entire Hilbert space, right? Because it doesn't contain vectors that have infinitely many non-zero coefficients. For example, those vectors whose coefficients quickly decay, like, for example, the vector 1, 1/2, 1/3, 1/4 from above is not in our domain here. So you see how subtle things happen here. And you may wonder, well, how does this really come up somewhere, this issue of domain and infinity and so on? Yes, as we will see later in the course, that sort of thing is, for example, is responsible. These domain issues are super important. They are responsible, for example, for the fundamental limit to the resolving power of a telescope or a microscope. It turns out that how well a microscope or a telescope can possibly resolve an image depends on the opening size of the telescope or the opening size of the objective of the microscope. And when you translate the opening size, the so-called aperture of your telescope or microscope into the resolving power, the sharpness, the maximum sharpness that this instrument can achieve, then you run through a calculation which in fact is fundamentally a calculation of a dense domain in a Hilbert space which does not span the Hilbert space, or even a non-dense domain. Sorry, dense, I should say, a domain is dense if none of the vectors in the Hilbert space is orthogonal to our domain. So let me say here, because of this, these are all in df hat and are a Hilbert basis, right? Hilbert basis. Therefore, we say that df hat is dense in H, and we write for that the df hat, and then we put a bar over it, and that bar means completion. That is the Hilbert space. Okay, so that's just a bit of terminology. All right. This was just a word of caution. We need to be careful when we have operators or linear maps on Hilbert spaces, because the infinite dimensionality means that we need to be careful. Our linear maps may not be able to act on all of the Hilbert space because they may map some of the vectors of the Hilbert space outside of the Hilbert space by having images that are not normalizable. So we always have to restrict the domain of an operator such that the operator maps the vectors into normalizable vectors, that is to say, into vectors that are in the Hilbert space. Right, now, what we were aiming for is changes of bases in the Hilbert space. Changes of bases. Okay, let me remind you. Recall. If f hat is operator, then we can look at the matrix elements of f hat in a basis such as the Bn. So the matrix element of f hat are Bn, Yn, it's R, f hat, Bs. Okay, and let me remind you that in this way we have expressed the concrete matrix elements in terms of the abstract linear map f hat. But we can also go the other way around. We found that, and vice versa, we found that f hat is then equal to sum over R and S. And then we had here B R, F hat, RS, and then BS. And we calculated that with resolutions of the identity. Just go back for a few minutes and then in the video and you will see how we derived that. Okay, so let me remind you that this is what we had when we went back and forth between abstract operators and their matrix representations. Remember that the f hat could be any operator, x hat, p hat, whatever. Now, we are interested here in change of basis maps. The f hat is arbitrary maps. Now we look specifically at a change of basis map. So consider a change of basis map. And let's call it, say, U hat. From a basis of Bn's to a basis of Cn vectors. So what our change of basis map is doing is it is mapping vectors Bn into U hat, linear map, acting on Bn. And the output of this is what we call the vector Cn. Of course, we will want these bases to be Hilbert bases, so in particular also normal and so on. Now, U hat is a linear map. Linear map. So it can be written in a basis in this way, or in this form. Let me show you. Here, we have that if f hat is a linear map, then it can always be written in this way, where these coefficients are given by these matrix elements here, right? Evaluated this way. So now let's do this for the linear map, which is U hat. So what we're saying is that U hat must be of the form, being a linear map, it must be possible to write it in this way, choosing the B basis. U hat RS, remember these guys are just each individually complex numbers, and then yes. Now, what are they? Equal to what? Well, let's look at it. Here we have it in general for all linear operators f hat. We have that f hat can be written in this way, and this coefficient matrix is given by that. So we have that. Oh, where's the cursor now? Ay, ay, ay. Sorry about that. My writing software tends to crash. All right, so I had to rewrite the last equation here. Okay, so we have that the U hat operator, the change of basis operator, from the B basis to the C basis can be written in this form, where we have that the matrix elements U hat RS are given by BR U hat ES. Okay, now let us remember that U hat acting on a basis vector BS gives us a basis vector in the C basis, right? That's because of this here, right? When you have U hat acting on a B basis vector, you get the corresponding equally numbered C basis vector, right? So what this is telling us is that this is actually, so we have, therefore we have that U hat RS is equal to BR, and then what is this? This is CS, right? This is CS. This is this. All right. So this is what we have now here discovered, namely that the matrix elements of the change of basis linear map are just given by the overlap, by the inner product of the new and the old bases. So what does that mean if we want to change bases in a Hilbert space? Well, therefore, change of bases looks like this. And a change of bases looks like this for vectors. And I will leave it to you to look up or to calculate yourself how the change of bases works for matrices. I think I have an exercise for that as well. Okay, so change of bases, how it looks like for vectors, we have that psi in a basis is 1 psi, and that's the last time I'm spelling it out in all detail, but this needs to be absolutely clear. So I'm doing this one more time here. Psi, this is psi n, the wave function. So this is sum over n, and then the psi n and the bn. We use the trick of the resolution of the identity in the B basis here. But we can do the same thing with the resolution of the identity in the C basis. So now we have sum over m, and then we have Cm, Cm, psi. These coefficients are another wave function that we may put a tilde on to distinguish these coefficients. So this then is the sum over all m, and then we have the psi tilde m on the Cm basis. All right, and the question is, how are the psi n related to the psi tilde m? That's the question here. Well, let's just calculate it then. So we have that psi n is equal to Bn psi, right? That's the wave function, which we can write as the sum of, which we can write as Bn, and then we put an identity here, psi. And then we can spell out this identity in the C basis, sum over m. And then we have here the Cm psi. This is the wave function psi tilde m in the C basis. And what do we have here? So we have here that this is sum over m, and then we have these overlaps here, Bn, Cm, and then psi tilde m. But let's look at what we had above about the U matrix. We have here that the U matrix consists of the B, C overlaps, with inner products between the B's and the C's. So therefore, this is actually equal to the sum over all M. And then we have here this U hat change of basis matrix and its matrix elements N and M acting on the psi tilde M. Let me just spell out what we have on the left-hand side. We have this, and therefore we have now found the relationship between the coefficients of a vector in the B basis and the coefficients of the same vector in the C basis. And similarly, you can work out, and I encourage you to do this, what the relationship is between the coefficients of an operator, of a linear matrix, in the B basis and in the C basis. A little hint, as you may expect, you will have the matrix U occurring twice in this. Okay, so this is it for today, and I wish you a nice weekend.